Fantastic. Welcome, everybody. I'm talking today on the subject of thermal analysis in maintaining good distribution practice, and it's the first one of our thermal talks. So I'm going to share my screen. Cool. Well, thanks for that, Chris. And if I can ask colleagues, if you've got your microphone on, if you can press mute, that would be great. But if you want to ask questions as I'm going along, please put your hand up, and there'll be some time at the end of the presentation for discussion and answering questions as well. And what's the real aim of these talks? Well, the aim of these talks is to give a little glimpse in the different areas where thermal analysis is being used and applied. Some of the talks will be more grounding about some of the principles and application, and hopefully some of the talks will be around the cutting edge to get people's imaginations going in terms of, yeah, I could apply that new approach to my problems and issues in samples. So let's hit the first one. So thermal talks will be bi-monthly, and we'll spotlight the latest thermal analysis and calorimetry. And hopefully we'll bring a really diverse audience together, because us lot doing thermal analysis, there's usually one or two of us in an organization, and it's quite lonely sometimes, and sometimes you just want to ping a few ideas and have a chat. So that's one of the other reasons for doing these thermal talks. Hopefully these presentations can ignite some interesting conversations and increase the networking within the group. Sometimes also we highlight sort of newer early career researchers, because again, it's quite hard now, to get the money to go to these conferences, because everything's gone on Teams since COVID. And again, working in thermal analysis, sometimes your ability to network is not as easy if you're in a slightly sort of more fashionable and high impact area of chemistry. But the thing is, hopefully today and throughout these talks, the point is to show how ubiquitous thermal analysis is, and how essential it is for many of the aspects that are involved with the Royal Society of Chemistry, material science, I don't know, stability testing, looking at extensive reaction, polymer food, pharmacy, energetic materials, and everything in between. So hopefully these talks will touch on that. So as I say, the aim is to grow a community, advance the network, and we want to learn and innovate and collaborate. And that's the point of these talks. So what am I talking about today? I'm really interested in using drones to increase the access of isolated communities to healthcare and medicines. And that definition of isolated can mean I'm on an island in the middle of nowhere. I'm on an island that actually has all the facilities that you'd expect. And I'm talking about the Isle of Wight here, but they get their medicines now over on a ferry or a hovercraft, and if that stops, you've had it. And there's other interesting aspects that, in terms of feedback and making sure that your patients are healthy enough to take particular medicines, has become a bit of an issue there. Or it could be geographically isolated. You may be in an area that doesn't have all of the facilities, and so a drone can deliver something to you. And the reason why putting medicines in drones are interesting is because medicines are high impact. They tend to have low stability or short expiry dates. Many of the important ones do. Many of the important life-saving ones do. And also, they're very light. So putting loads of medicines on a van has quite high environmental impacts. So we've done a bit of work where we've just measured the mass of things. And if you go into palliative care, the average mass of the medicines that somebody would take towards the end of their life is probably daily between about 50 and 100 grams. So you don't need to have huge, great deliveries of stuff, and we can deliver things directly to people by drones. There's a certain advantage there. So really interested in this. There's a diagram here that's quite interesting. And this is immediate now. Why is thermal analysis important? Well, drones fly in the sky. they like to be made out of trendy materials, carbon fiber, lightweight, strong. And people like, when they're designing drones, to express that. So they want to show all that engineering stuff. So usually that carbon fiber is on the outside and people can see it rather than painted and concealed. Carbon fiber is black. Carbon fiber absorbs sunlight really easily. Drones come from a survey. Drones were developed recently. Drones have been around for the last 100 years. They've been used for helping spot things on balloons, and I think the earliest drone was developed towards the end of the First World War, in terms of helping pilots improve their shooting skills, because obviously you don't want to shoot down a real person in a biplane. If you've got a drone to do that for you, you can then practice. But with these smaller drones, they've been used a lot for surveying and camera work and image taking. And by doing that, you have a gimbal, and the pilots usually want to make the drone stable. And they usually want to have their aspects of things being the same. And what we've found by looking at this flight crew here is that they fly with the drone at the same angle to the sun, going back and forth, because they're used to that, because usually there's a big camera on the front and they're trying to take a nice image of something. So they're looking at a Top Gear car doing some fantastic maneuvers. So the drone itself is always pointing in the same direction to the sun. We found here that actually one side of the drone, and this was on a November day in Billericay of all places, that side of that box was heating up to quite high temperatures. And so a simple conclusion from this very basic thermal analysis, which is point a thermal camera at the drone. There's a little story about this. I turned up with my very small drone that does have a thermal camera on it. I wasn't allowed to fly that day because the wind was a little bit too high, so we could use the bigger drone, but I still used the thermal camera element. I was holding it literally under my arm like you would do with a small dog, and we got a nice picture there. And so the impact was, move your box relative to the sun during a trip, paint your box with shiny material to deflect the sunlight rather than absorb it. Because if you've got, if we look here, I've got different temperatures. I've got 6 on one side and 26 on the other. So I've got a 20-degree temperature difference because it's a really cold day. Then I'm going to get airflow inside the box. I'm going to get gradients that could cause us all sorts of problems. So that's application of thermal analysis directly on the day of doing a flight. What else do we have to worry about? Well, we have to worry about, will the medicine that we want to deliver get there safely? And will the quality of the medicine be maintained? And I've shown this on various talks before. If you want to attract the Metropolitan Police, take some vials and strap them to the leg of your drone so they look like cartoon sticks of dynamite. And we did get a visit from the Metropolitan Police asking us what we were up to. This was at the very start of our drone journey. And I wanted to look at something that was very, very useful. And there was reports that there was in Wales, there was a pharmacy that was isolated because their bridge had been destroyed during a flood. And I think it was in North Wales. And the car journey was an extra 30 to 40 minutes. And there was some diabetic patients that weren't getting their insulin. So we thought, insulin's relatively unstable. Let's chuck it on a drone. Let's see how unstable it is. And even just flying on a normal day, we flew everything around and we did the pharmacopoeia tests, which is essentially looking at it with UV light to see if things have aggregated, because obviously we've got proteins, and proteins are like sort of butters and fats. If you shake things enough like milk, you can then make butter. So those hydrophobic things come and agglomerate together. And the same thing can happen with biopharmaceuticals like insulin, those kind of peptide and protein molecules. You can shake them apart, they denature, they twist open. Hydrophobic parts don't like water, they come together and aggregate, and it won't pass the quality test. It won't actually be active anymore. But bizarrely, we did a load of flights and it survived. Published a paper on it, and then did really, really well with that. We got lots and lots of citations. However, members of the drone community then told us all the different rules we were breaking. So now we've sat all of our professional pilots licenses, our exams, we're all qualified, and we tend to, my little research group now tends to work with drone operators. We tend not to fly the drones ourselves, but we tend to worry about the cargo. But sometimes we do fly. This is just a final slide. I hinted at it earlier on, looking at the impact of extended kind of logistical pathways. This worked to treat until COVID, then there was issues around COVID, but also on the Isle of Wight, we have an aged population, higher frequencies of cancer. So the Hospital St Mary's used to make up these IV or subcutaneous injections, the infusion bags or the syringes that you see in their own manufacturing unit within the hospital. And you have to do that wearing masks, in isolators, so you don't get any biological contamination. Because there's no preservatives in any of these formulations. Vidasa is one example here that we've got shown there, but many others, cisplatin and all the other types of chemotherapies. And so we have to do it very, very carefully. And putting things in isolators, putting people in suits and masks and training them and doing them in clean rooms with lots of filtered air and under lots and lots of control is expensive, demanding. The training takes long, and it's a really uncomfortable thing to do all day, wearing these big gloves in a box, manipulating things. So for various reasons, they closed that facility down in the Isle of Wight, and now things are delivered via the ferry. But going back to our aged population, if that person is for everybody, if you're suffering cancer, you are open to other infections. If you turn up with a cold or a cough and snivel or a high temperature, you may be refused your chemotherapy or your monoclonal antibody treatment because you're not healthy enough to take it that particular day. The problem is the expiry dates of these things are in hours. The expiry is usually 24 hours or sometimes 48 hours. Sometimes can be even less. Like I think for data, I think it's like 12 or something. I think I've got it written down here. Oh yeah, the expiry is 8 hours. So you would tend to then, if you had your manufacturing unit in the same hospital, you would tend to phone up to the manufacturing unit and say, please halt the preparation. My patient can't take it anymore. And that's fine. Come back next week. Great. If things are coming from Portsmouth, as in this model, the preparation's already been made usually when the patient's being consulted on the morning of their treatment, and it's making its way over. So now they can't take that medicine on the day. They have to come back a week later once their temperature is down. But the expiry is only 8 hours, 24 hours, 48 hours. So we can't use that medicine anymore. And the other thing with chemotherapy for patients, it's based on a height, mass, and surface area ratio of the patient. So my dose will be different from my wife's dose or your dose because we're all different sizes and shapes and weights. And so you can't use that medicine for anybody else. So you have to throw it away. And as demonstrated here, these are extremely expensive. So just for this particular hospital, they're losing between £20,000 and £30,000 worth of medicines per month because of patients presenting with high temperatures, coughs and snivels. They can't take their medicines, but now they're being thrown away. We've benefited it as a research group because we're using some of those medicines that can't be used for patients in our research, but still it's an appalling waste. Can we use drones to avoid that? So we can then fly just within 30 minutes rather than the 2 or 3 hours it takes by this method, and then we can be a bit more reactive. What are the things we have to worry about? As we say, dangerous goods, coordination, the packaging. Is there other things going on? Acceptance from the regulator. That's the civil aviation regulator or the medicines regulator, which is the MHRA. And then we've got to think about service interruptions and all sorts of other things. And taking it back to this talk, because I've gone a bit off, I've set the scene. We've got to make sure that we maintain good distribution practice. When I'm moving those medicines, I need to make sure there's a minimum standard that are met, that the quality and the integrity of the medicine is not changed, is maintained through that process. And here, the distributor would be our drone operator that's flying the drone. So they need some evidence. So good distribution practice. We must ensure that the medicine supply chains are authorized in accordance with the regulator. Here I've got the European Union. They're stored in the right conditions, so therefore at the right temperature. Many of these medicines are required to be stored between 2 and 8 degrees. Some of them are required to be stored between 20 and 22 degrees. These are things with poor solubility, and if we lower the temperature, we may get precipitation. We've got to make sure we get no contamination. We've got to make sure that we have good turnover with the stored medicines, and we need to make sure things are labelled properly so we don't get any confusion there. And the other thing we've got to make sure is the distributor is tracing what's going on. Now, the one advantage of drones is that's done because there's tons of data. The positioning data of the drone is recorded and actually usually made available. If you're getting permissions to do professional flights with the CAA, you can use one of these flight trackers that you look at normal crewed aviation. You can see this with uncrewed aviation as well, because there'll be a transponder on that. So how does thermal analysis fit into all this stuff? And how does it fit in with maintaining good distribution practice? We need temperature control in our box. You saw that on this figure here. We have a box, we put things in, and we put these ice packs, these phase change materials in there to maintain the temperature. Oh, I think there's a question that I haven't got the chat on.
You lost slides, Paul.
Oh, sorry.
Yeah, sorry, the slides have gone.
Oh, the slides are gone. Oh, I do apologise. It's me chatting away to myself. Are we back on the slides?
Yep, we're back.
Oh, brilliant. Tell me off. That's good. Right, here we are. So thermal analysis, how does it fit in with good distribution practice? We need to control the temperature. We need phase change materials. And the simplest one is ice, isn't it? It goes from solid to liquid. And while it's going through that process, the temperature is going to remain the same at 0 degrees. We need to monitor the temperature. We need thermocouples. We need data loggers. And sometimes we need thermal cameras as well. And we need to do stress testing. We need to simulate these things in the lab, so then we can show that our medicines can survive and we can give a specification. This medicine needs to be held between 2 and 8 degrees. This medicine needs to be held at 20 to 22 degrees. Or in terms of the COVID vaccine, this medicine needs to be kept at -80. What's the implementation for drones? We need to equip things with temperature monitoring systems. We need thermal packaging. We need phase change materials. We need light phase change materials. We need to do some flight trials and lab simulations, and we need to put all this information into some kind of audit trail. And now we're going to get back to thermal analysis, because you know this, don't you? We go on picnics. We put things in picnic hampers, and we make sure that the temperature of our, I don't know, our cheese and pickle sarnies is maintained by putting in an ice block. And these are these phase change materials. What are they? They're things that go from liquid to solid and solid to liquid again. If I cool the temperature down, things freeze. That's a solid. As I raise the temperature, we get to the melting point, but we know as things melt, the temperature remains the same. And what we're making sure here is, can we make some materials, encase them, use things where we can maintain that temperature while things are going through their phase transition, and then they are liquid again. And the other thing we have to do, it's just like at home, the same thing with these medical cargoes. Just like your cheese and pickle sarnie, we've got to put it in the fridge again, cool it down and redo it again, because we don't want to be throwing all this away, because it's got a huge environmental impact, and we want to see if we can do this repeatedly. If we're going to do it repeatedly, we need to do some stability testing on the phase change materials. So how many times can I go freeze, cool, freeze, cool, freeze, cool, and still maintain the integrity and the safety of the phase change materials? And this is a VersaPack here. This is the typical thing you would see moving stuff within a hospital and between hospitals. And I think if you see a red one, that's where you see blood units on the back of motorbikes. That'll be a VersaPack. And in there, there'll be phase change materials to make sure the temperature is within specification. So, right, so this is a little bit of work done a few years ago now by a fantastic MSc student called Hersley. And we did some just preliminary analysis working with a company called Intelsius. And we're looking at methyl laurate. So it's a material that you make up with water, and it's got a melting regime of around about 2 degrees to 3 degrees. And because it's an organic material, its thermal conductivity is low. So it actually takes a bit of time to freeze and melt, which is what you want. You don't want things to quickly melt and quickly freeze, because then it won't allow that sort of temperature control for a long time. But because of the low thermal conductivity, you need a big block of it as well. So for drone stuff, this gets a bit tricky. And the other thing is with these organic material, there is the potential for decomposition if I do lots of heat cools, heat cools, heat cools. So what have we got? There we go. So we did some DSC, and they're the parameters there. We equilibrated at -20. That's like freezer temperature. And then we heat cooled, and we used some aluminium T0 pads. And we used an off-the-shelf phase change material. And this is called Wagnerlol, which is methyl laurate, which is that. And it's got a dye in it. Why has it got a dye in it? Because these things are carrying medicines. If you drop it, you want to see that the dye has come out, and then you can reject the whole of that load. If it was just methyl laurate, it'll look like water. So if you had a leak, you wouldn't know. You just think it was condensation. So this is why we put in this violet color here. And I think it's probably something that's generally regarded as safe. It's probably got an E number as well. And that's got quite a high melting point. But of course, if we had a small amount of something to methyl laurate, we're going to lower the melting point of that. And I've probably given the wrong impression here. We're looking at pure methyl laurate. That's the stuff that's going to go into our ice pack. We did some just initial DSC. We didn't recalibrate for the different heating rates. It was just to have a look at what's going on. And this is the melting point of our methyl laurate. And we're using a recommended standard procedure here. And as you can see, as we start to reduce the mass, the size of the peaks go down. And there's not too much change on the onset here. And what's interesting is, of course, when you're looking at this material, you guys will get grumpy because, oh, the peak's really wide, but we actually want a wide peak. We don't want things like indium that has a very narrow melting peak, because that's the point of having these things that have low thermal conductivity, because they're acting as phase change materials. So we want them to spend a bit of time melting, because that's when we're actually controlling the temperature, which is good. This is really basic, and I forgot that people may not be aware of this, so I've pinched a couple of these from the internet. But if we're going through a melting, and this is looking at a change in a protein. But if you think about this, the products and the reactants, we're essentially, if you've got a DSE curve, we're looking at different points in that reaction profile. If I look here, if I stop here, we can get different amounts of A and B. Because if I take the area of the whole peak, that will tell me that that area relates to all of B, doesn't it? And so if I take a ratio of the area at the end of the peak at different points, it'll give me how much A and B is present, and I can get the equilibrium constant. The equilibrium constant. And if I get the equilibrium constant, then I've got a ratio of how much of A and B is present. Then I can then go to, and that equilibrium constant, of course, is changing as a function of temperature. So then I can do some basic Van Hoff plots here, which is log of the equilibrium constant against 1 over the temperature. So Van Hoff. So it's a bit more sophisticated. I've gone through the very, very basics here. I mean, you can read through that slide at your leisure, but essentially there's standard techniques within all of the software of DSCs where you can do purity calculations. But there are a few assumptions. Essentially, what's happening here is you're chopping up your melting peak, and then you're plotting those ratios of areas against temperature. You're doing a little bit of normalization, and you're getting a straight line, and you're looking at that straight line, and then you're measuring. You've got to put in what you believe the relative molecular mass is. In this case, we've made an assumption that it's the relative molecular mass of just the pure methyl laurate, and we have to have things that are relatively pure. So things that are around the 98.5, because we know impurities lowers the melting point of things. It's a colligative effect. That's why we put salt on the road. So the melting point of ice is not naught anymore. It's like -2 or -3. So what we're doing here is we're using the DSC to measure the purity, and then we're doing some temperature cycles. and then seeing if that purity level is maintained. Okay, and this is just the methyl laurate on its own, and luckily it's, well, no, I think this is the methyl laurate with that small amount of dye in. That system, luckily, is just about above that cutoff, so it's 98.86% pure. So we've done that analysis on that material there, and then we've started to look at different things. So we've looked at different masses, and we've blown this peak up a little bit, so the range here is quite wide, and we've equilibrated. We've isothermal for 10 minutes, we've heated it at 1 degree per minute, and then we've ended it at 20. And we've kind of got that as we start to go big, we start to get deterioration in our peaks, and the longer it takes to melt the whole sample. And what we're trying to do here is not to try and do optimizing a big lump of our phase change material, because you want that in your cool bag doing its job. What we want to do is we want to apply that Van Hoff analysis to make sure it's still pure after a number of, or the similar purity after a number of heat cool cycles. So actually adding small amounts is good. The next thing then we actually looked at the mass of the loading, we looked at the enthalpy, we looked at the melting point, and so we extrapolated back to a theoretical level which was quite close to the published values, and so we decided to go low in terms of the mass loading there. And then we've gone from, oh, hold on, what's this one? So this is gone, we've used the purity and enthalpy Van Hoff approach, and then we've got the purity, and we've theoretically calculated the enthalpy here. And again, the purity, as we decrease the mass load, is getting closer to a value of 99. So we've added a caveat that we want to go between 1 and 2 milligrams in our experiments. And then the holding time is quite interesting, because things like indium that you're familiar with calibrating a DSC has got really good thermal conductivity. And so it freezes and melts really, really quickly. Whereas this stuff is designed not to have it. It has low thermal conductivity. So the longer you leave it in the holding, more of it actually freezes. So we found in our experiments, you have to leave it for a little bit, isothermal at the -20. We still get similar purities, but the enthalpy is affected by that. And that makes sense, isn't it? It's how much of the stuff is actually then melting, giving you that melting enthalpy there. So holding time's important, is essentially that one. So conclusions: smaller loading mass, more precise and accurate, slower heating rate recommended. We got good purity values. We repeated the calibration at 1 degree C, because now we're getting things that can fit. And then we have to, for these phase change materials, when we're doing these kind of experiments, we need to leave it for at least 30 minutes. And then what have we got here? I can't give you too much of the details, because this is we actually then applied that approach to a whole load of materials. These materials have been heat cooled in their own laboratories 200 times, because again, if you're making things for drones or any kind of medical logistics, you don't want to throw everything away. You want to make sure that your phase change materials can survive. This has been heat cooled 200 times. It's still the same Royall stuff, and our purity has been maintained. So the take-home message is we can use DSC for looking at the performance of phase change materials. And the next thing you want to do, which we haven't done yet, is to start to look at, can we then develop new phase change materials to show similar properties, similar performance in lots of heating scales that we can use for our drone deliveries. What's the next thing? We mentioned simulation, and we mentioned good distribution practice. So I'm going a little bit away from thermal studies, but it's still important. Drones vibrate, I'm afraid. When you see Top Gear and the drones doing lovely sweeping shots of stuff, I'm showing my age now because Top Gear hasn't been out for many years, but these kind of sweeping cinematic shots using a drone, they tend to have a gimbal that dampens out all of that kind of vibrational interference. When you're putting things into the drone, you're going to suffer that. And of course, when you get the drone out of the box, everything's fine, but the rotor blades will eventually get pitted, and will start to degrade a little bit. They've all got a certain working life. After a number of flights, it's usually 100 or sometimes 500. You replace the propellers. But in doing so, just before you get to that point, there will be vibrations. We were worried about this, so we had a look at our monoclonal antibodies. Monoclonal antibodies are a bit different from chemotherapies. That Vidasa example I showed you, you would have a regime of, say, 4 weeks of injections, 1 week off, see how you are, 4 weeks of injections, one week off. Because what you're doing there is you're killing cells. With a monoclonal antibody, you're using the fact that you can turn your own body's defenses onto the cancer. So the antibody bit will then start to lock on to the cancer, and then your body recognizes it as a foreign thing and starts to kill it off. So for monoclonal antibodies, you tend to have one infusion. So again, really important to make sure that the patient arrives with that. And these things are orders of magnitude more expensive because they're grown in mice, essentially. And so each one of these infusion bags can be between £5,000 and £30,000. Cost benefit means only one procedure, and you can save a lot of people's lives with it. But we have to deliver it carefully. This is why these experiments are so important. So we looked at size exclusion, which essentially is small things get stuck in the column, big things pass through. Small things are retained, so the high molecular weight fragments, the high molecular weight bits there go through. The low molecular weights are here. And we're looking at the monomer, so we're looking to make sure that we've got this going on. Because if we shake it enough, some of those arms can come off in our monoclonal antibody. You never get a completely pure material, but the specifications are that if we have enough of the monomer, that's okay for the patient. If we shake enough, those fragments can come together and aggregate, and we can use dynamic light scattering to then get an idea of the aggregation. And essentially what dynamic light scattering is, things that are bigger have a slower diffusion. If I fire light at them, they'll scatter the light in a lower frequency pattern. So actually the change in that kind of scattered light will have a lower frequency in its change. If things are scattering about, the intensity would change more frequently. And then you can relate that and you can calibrate that in terms of diffusion coefficient. If you get diffusion coefficient, you can work out the size. That's light scattering. We did horrendous things for the monoclonal antibodies. Really important when you do any stability tests, and that goes for thermal, all sorts of thermal things. It can be mechanical. Explore the edge of failure. Make sure if it does fail, you can measure it. Quite often when I viva people that have used things like HPLC, they'll say the peak is the same size, so therefore it's stable. And I'd say, have you degraded it to make sure we can see where the peak disappears or we get two peaks and other things? And quite often they say no, which is a little bit scary. So we've taken some of these monoclonal antibodies. As I say, they're really expensive. These ones here are used to treat all sorts of different cancers. But because they've reached that very tight expiry, we've actually then got them quickly the day after into our labs, and we've shaken them to death. And this is a very basic model of high vibration. And bizarrely, you can do some really horrible things to these monoclonal antibodies. We can vibrate them for a number of hours at different temperatures, but each one, we made sure we could detect failure. Bizarrely, with this experiment where we're looking at the aggregation in our size exclusion, it fails, then it recovers again. And what's happening is we're breaking apart the aggregates. We then went on to use our size exclusion, and then we've got stability measurements there. And what we've got in these experiments is now we're moving to the drone. So we've looked at the control that's stored at 4 degrees. We've flown in smaller decanted samples, and then we've also flown with the full infusion bag. Because we don't get so many of the infusion bags, we wanted to split them up a little bit so we can get some really good statistics, and then we flew the infusion bags as well. And what was really nice, they all passed during the drone flights. And those were the drone flights that using this platform here. And that I think is called a V50. And it's got a wingspan, I would say, of probably about 4 meters. So it's quite a big thing. We would call that a 0.2 Andy drone. Why am I calling it a 0.2 Andy drone? When we start off with some of the papers that I've done, we were using a drone by Wind Racer, and I wanted to take a picture of it and show people the size of it. Essentially, that's a small plane. they were grumpy because there was quite a lot of IP. So I said, can my colleague get into the hole so we can demonstrate the size of it? And they're okay with that. Andy was 6'1" and he fitted perfectly in the hold of the Wind Racer, and that became a 1 Andy drone. So you can see here that now this one is a 0.2 Andy drone, which is kind of funny. We've got our own methodology there. There we go. So we looked at the vibrations because we put vibration data loggers in the drone, and we measured the drone doing its stuff, which is various different takeoffs and landings. And we've got some interesting characteristics here. There's differences between the vibration on the drone and inside the VersaPack, because the VersaPack actually dampens down quite a lot of the vibrations. But essentially, the largest vibrations which was about 63 hertz, which is influenced by the type of rotor and the speed of rotation. Different drones, different platforms have a different arrangement of the drones. You get constructive and destructive interference with the vibration. They have different size of propeller. Sometimes they use liquid fuel, i.e. kerosene and petrol, or they use batteries. So each one will have a different vibration architecture. So we need to do these measurements for different types of drones. But this is an older RAF station in Thorney Island. It used to have Typhoons. It was heavily used in the D-Day because they flew over from there. It's not used anymore, but it's a great place to do drones in a controlled way. And essentially, we showed we could fly that. That was our route for our drone, our flights with the monoclonal antibodies in. And with all that data, we got a nice letter from Rob Lucas, who was our quality assurance manager. And he basically said that I'm happy, it's meeting good distribution practice. So I'm going to zip through really quickly now. So we've done vibrational logging for lots of different types of drones, and we're starting to develop a library there. We're now starting to develop a replication study where we've got these different vibrators in our laboratories, and we can start to then mimic lots of different drones. And what we're also trying to do is mimic things like bicycles, cars and vans. In London, a drone is probably not the best solution. A cargo bicycle probably is, but not when it hits a pothole. So its frequency is going to be 1 or 2 hertz, but the G-forces could be quite high if it hits a pothole and goes down. So we're starting to develop that. Very quickly, if a drone lands in grass, it may be infected with stuff. We've got to make sure we can disinfect our drone. If we're using our drone with medicines that are antibiotics, which is, I don't know, the next pandemic outbreak, drones are good for breaking chains of infection. So we have to make sure that when it comes back, it's not infected. We need to clean it. This is a colleague, Nazira. She grew up, I don't understand biology. It scares the living daylights out of me. But she convinced me that this particular type of E. coli, DH5 alpha, will only grow on this particular type of growth media that's in these Petri dishes. So if I drop it, I'm not going to die horribly. But it's a very good model for E. coli out there. And what we wanted to do, can we disinfect our drone? Well, we can disinfect our drone. We can put it into an autoclave for 121 degrees for 15 minutes under 100% saturated steam. Problem is the drone will never fly after that because all the circuitry will be destroyed. So we'll have to surface disinfect it. And a good way of doing that is using UV, or we can use industrial methylated spirits, essentially alcohol, or we can use industrial methylated spirits with chlorhexidine in. The one thing we're worried about is that lots of plastics are used in the smaller drones. We quite like the smaller drones, as I said, because the size of the cargo is quite small. So if I'm covering everything with this to disinfect it, it could affect our glass transition. And we had different types of polymer here. And this is the elastomer. This elastomer is used on hinges, connectors. It's kind of the squidgy polymer that's used a lot in the construction of the harder types, but it's still really important to analyze. And it's got a glass transition about -50, so it stays below that. And basically doing UV, chlorhexidine, or just ethanol didn't affect it. What was really interesting though, if you cover those pieces, because what we did is we didn't put a whole drone in, we just cut pieces of the polymer, put it into a Petri dish, exposed it to the E. coli, and then did our washing. And essentially our washing was put in a bit of those liquids, turn it out and see if it survived, or put the UV light onto it We discovered that actually you've got to leave the UV light on for about 20 minutes, UVC light, to kill things off. It wasn't as robust as dipping it in IMS or with the chlorhexidine. The next thing is nylon's used a lot for the propellers. And we do have a problem here because there's a little glass transition about 38 that we've got to be careful of. And so the idea is, again, we killed off most of the bugs with IMS and the UV light. But if you are using surface disinfection with those solvent-based things, you've got to allow the solvent to evaporate off so we don't lower that glass transition there. Carbon fiber is interesting. It's really hard to get into a DSC pan. So we used a DMA, a dynamic mechanical analyzer, and we got a glass transition here at about 125. And essentially, that's the glass transition of the resin that binds everything together. But again, we felt that using surface disinfection would not lower that glass transition too long. So the idea is we can use surface disinfection, but we need to make sure that everything evaporates off at the end. So lastly, what we need to do there is we need to start to develop new packaging, and it'd be great to have a unit load device, and it's got to conform to all the regulations. If we're creating new unit load devices, the kind of thing you pack your suitcase in when you go on your holidays, it's the same thing we want to do with the drone, so we can just take it off and move it around the hospital, not worry about unpacking things from the bag. We've got to see if the temperature's okay. And I thought data loggers worked, and I thought you could put them into the bags. And this is a data logger, and we can range the data logger in different ways and have different numbers of phase change materials and investigate how long it takes to maintain a certain temperature. So what did we do here? We packed it at room temperature. We put everything in and put it then at 40 degrees, well, 37.5. Why did we do this? Because I'm working with Matadei Hospital in Malta. They want to deliver some of their aseptic medicines to the island of Gozo, which is about 30 kilometers away, because patients have to get on a ferry, just like the Isle of Wight. And so they want to see if they can deliver their medicines with drones. Malta gets very hot. Can we measure what happens when we get to high temperatures? And it does take a lot of time. So if we start to look at all these different data loggers, the data loggers themselves have a certain lag time. So if I put my box, and what we're doing is we're recreating what would happen in the aseptic units. They'll take a bag at room temperature. They'll take the medicine that's in 4 degrees. They'll take some ice packs and build it up. But it takes the data logger then some time to recover its temperature. And this one, temperature monitor, this one only had, I think, 1 ice pack. And I think this one, this was a Versa pack. So it only had 1 ice pack, and it wasn't very good. We had a different type of bag, which was smaller, which was called a GPO bag. And that managed to maintain the temperature just fine. And we're interested in making sure that the temperature is maintained between 60 and 240. So essentially the advice here with this very basic thermal analysis, which is measuring temperature, is put everything in, apart from your medicine, leave it for at least half an hour, put your medicine in, and then you can fly for at least 2 hours. Because remember, you've got to load it onto the drone, you've got to take it off the drone, you've got to move it through the hospital, and so we're nice and safe there. The reason why Malta is really worried about this is because they treat their patients with their manufacturing unit really close by. So a porter, we've seen the porter, I think his name was Richard. He would move from the aseptic unit with the infusion bags, the IV bags, on a trolley, all wrapped up carefully, and it would take about 5 minutes to get to the patient. If you're moving through with things with drones, there's more time to get to the drone itself, the takeoff and landing, and then back into the Gozo hospital. So that window there, they're happy with. We started to use mean kinetic temperature, which is good for long-term storage of things. But actually talking to a few of the MHRA people now, they feel as though for the kind of 1 hour, 2 hour trips, mean kinetic temperature is not correct. Mean kinetic temperature is based on the Van Hoff type principles as well. And we're looking at a first order degradation reaction, and we're making an assumption about the activation energy. Activation energies for most degradations is around about 80 kilojoules per mole. And that was giving me all sorts of values there. But what we found is we definitely need 2 ice packs for everything. And we definitely, the GBO outperforms the Versa pack. But remember, for those medicines, we need to maintain 2 to 8 degrees. And for that particular orientation, we can do that within over 4 hours, which is just fantastic. So conclusions. Oh, and I've got 10 minutes left of questions. That works out very well. So our monoclonal antibodies are stable to drone flight. UV can be used for disinfection. Surface disinfection works well. We need to maintain good distribution practice for temperatures for at least 4 hours in our Malta application that I mentioned. Higher temperatures difficult. We need a better design of cargo box. We can use DSC to look at the performance of our phase change materials. But the next thing we're going to do is we're going to start to develop different types of phase change materials that have a slightly lower mass. And that could be things with using sort of networks and fibers and films rather than a big block of stuff. But data loggers do have a lag problem. And hopefully that was good for our first thermal talk. So thank you very much for bearing with me. I think we've still got everybody in the room, which is good. Do I have any questions? Oh, thank you, Ruth. I got a round of applause there. Thank you for that. Got a round of applause for Milan, which is good. Thank you, guys. Do you have any questions? Oh, Ruth, I've got a question from Ruth. Fantastic. Do you want to?
Hi, yeah, sorry you can't see me. My phone won't connect for some reason, so no camera. No, thank you very much for that. That was really, really interesting. You probably know that I'm going to obviously have a bit of a military use in application use in mind for this. So I appreciate you might not be able to say, but what if you're operating outside the UK? I know obviously you've been to Malta, and your temperature differential, if you're working, say, let's say in a hot sandy desert place, what sort of internal temperature would you expect on the inside of your box compared with the outside? What would it get up to?
That's very, very good. I can talk broadly.
Yeah,
in a project that we're doing at the moment. I've got a fantastic new PhD student, and we're going from the ground up. Literally, he's got data loggers on himself, and for the rest of his, can I say squadron? I can. I have to be careful because if I start describing things in detail, you'll know exactly where.
No, I get it.
He'll be visiting places that are very cold and places that are very sandy. Excellent. And we are literally measuring, because there's various medicines that the military will have about their persons. There's various emergency medicines that if you break your leg, and also in the worst case scenarios, if you get shot, the majority of injuries when people go on operations is you're jumping, running around, doing extreme physical activities. You've got a big pack on, you've got a bit of hardware that you've got to think, you're stressed, you get hot, and you can turn an ankle very easily. You can, break a bone. So they've got various different medicines that they take on themselves. Oh, I can be honest, it's called a fentanyl lozenge. You pop in your mouth, and we're very interested in the physical properties of that. And so the first step is, before we get to drones, we're just putting the data loggers on people, and we've got temperatures that are touching on 45 degrees in servicemen's pockets. But the other thing that's really funny, again, I have to be a little bit careful here. I thought they were all living in tents. They're not living in tents, because we worked out they're all back in air-conditioned hotels, because you can see, because they keep the data logger on themselves. And what was hilarious is we found out that many of them do spend a night in not hotels, but in accommodation with air conditioning, because the temperature went back down to about 20. But Ruth, if you think about some of the things that we're interested in, if it's just a solid dosage form, actually temperature cycling is not huge. If you think of an inhaler, many people in the services are asthmatic. They have an inhaler which is salbutamol sulfate for their a Ventolin inhaler for their asthma. That's actually a suspension. If you do these temperature heat cools, then the particle size is going to change, because you get Oswald ripening. The smaller particles dissolve faster than the bigger particles. So what happens is the size range starts to increase to the larger particles. And then you can't breathe them in so easily. So all this stuff's really, really interesting. So the drone stuff got me talking to people more in the defense side. I would never have done that. But the defense side has got some really interesting implications back to sort of civilian and healthcare in general. Cool.
Oh yeah, absolutely. Thanks very much for that. Yeah, we're absolutely obsessed with one-way effectors, as they seem to be called from time to time. So
Yeah,
just suddenly made me think. Do you ever do anything with regards to like sort of delivery on I don't know what they're actually called, remote control boats, for want of a better word, or are you just purely interested in air launch
Oh no,
drones?
the boat bit, absolutely.
Oh, cool.
Yeah. Because I'm spinning many plates, which is nuts. The Royal Aeronautical thing that I was in just before this meeting. There's a lovely lady in Oman. She's a world expert on remote everything, and she's found out we're doing drones that land because our islands are quite big and are populated. But if you go out to the Cook Islands and stuff like that, you want to fly a meaty drone, something that can fly for, say, 1,000 kilometers, and those exist. They're the kind of Reaper things, but they're the civilian versions of those. But the thing is, you still need an airstrip because these aren't VTOL; they're not vertical takeoff or landing. So absolutely, they're landing on water. And then there's other drones which are submersible as well, which are looking at aquatic life, environmental things and stuff like that. So absolutely. And then if you can deliver stuff on those as well, that's really good. So yeah.
Thank you.
Tony.
Hello there. As a thermal analyst of 42 years experience, a bit of fun for Ruth. I've just come back from Navy Leaders, where I've been talking about firefighting aspects and replacements for aqueous film forming foams. And of course, a lot of that is in the grounds of inorganic chemistry and replacements for halon. So there are many places where thermal analysts might crop up. So I didn't actually do any work for 35 years with thermal analysis. I guess as a first stab at these talks, brilliant stuff. I thought I was yards away from what might be called thermal methods, because I built DSCs and DTGs in the 80s at University of Leeds. I'd like to suggest for a future topic, maybe the committee, and I know there's a meeting at 3:00, what is thermal analysis, what it comprises, where it can be used, because I see that it's a subject which clearly with UAVs, thermal signatures are important. You talked about temperatures on different sides of your drone. I've also worked for the CAA, licensing aerodromes and aircraft and doing civil airworthiness. So thermal analysis get everywhere. So congratulations on the talk, and hopefully we can get this audience up to tens of thousands. Thank you.
Yeah. We'll start small, Tony. Really nice comments. Thank you for that. I think for that, then we don't necessarily have to have the kind of chalk and talk. The thing that I quite a lot of them, because it's quite nice to present things, with data and slides and stuff. Perhaps that what is thermal analysis bit could be a little panel that we could do and get one or two people from different areas and get some of the community to ask some questions, kind of thing.
Yeah, there's also something called the FAA microcalorimeter, because I do a lot of combustion work. Thank you for the London Underground symbol behind. I was the fire engineer for London Underground for 12 years, where choice of materials is really, really important. And also in submarines, I'm picking on Ruth really because she's got the military thing, but I'm sure others will do other aspects. There are loads and loads of places where thermal analysis crops up where it hasn't been considered. And if we can go to a small scale, I mean, I work on 3 meter by 3 meter furnaces and set light to trains. That's really expensive. I've also set light to the Airbus 380. That's even more expensive. But if we can do something on a small scale with a couple of milligrams and extrapolate it to a large scale, I'll be really keen on that. So I'll shut up now, let others talk.
No, Tony. Two things. You've done yourself an injury there, because you've dug a hole for yourself, because you're definitely up for a talk, because some of those anecdotes sound absolutely fantastic. So you're definitely up for one of those. I'm sorry about that, but there you go. I think the panel discussion is really, really good. And then I think that kind of what you wish, what we can do, is perhaps a challenge to some of the manufacturers. But no, probably not. It's about imagination. I think quite a lot of the kit we've already got is just using it in interesting ways. And just to finish up, I've got a whole load of things that I was reading on the train last night that I wanted to include, and I thought it's going to be a 2-hour talk, maybe one in a couple of years' time. But there's some really interesting aspects on how you calibrate thermal imaging cameras, and it's really interesting because it's still light because you're using infrared. You know this, but actually the way the light bends and the quality of the lenses, you have to. How do you get a calibration grid for an infrared camera? Is really interesting. You have those forensic things which are an L, so you can work out aspect ratios, can't you? Because if the L's skew width, you know that you're viewing it from not dead on. But when you've got a thermal camera, how because the light bends in weird ways. And then the next thing, of course, is fuzzy, and then of course it's diffusivity. So if you put a thermal camera on a drone, it's being cooled by the air. So actually, there's like a 5-degree error and stuff like that. And if you want to use a drone for looking at crops, it's really interesting because you're measuring essentially the evaporation for water. When you say the crop is water distressed, it means it's slightly warmer than the other bits of crop because that's allowing a bit of water to evaporate. But those temperature differences are 2 or 3 degrees. In a laboratory, you can easily do that with a thermal camera. When you do it on a drone, it gets really difficult. So there's lots of really interesting things. So I think one of the things would be great to invite some thermal camera manufacturers to give us a talk and tell us about what they're doing. Cool. Got a thumbs up there. Ruth, I've got a hands up.
Very quickly, just to flag, Nick's got a couple of questions. Well, I got a question for you in the chat. He's got no access to his microphone.
Oh, sorry.
Yeah,
I didn't see the chat. Well, what's the question? Here we go.
Oh, okay, shall I read it?
Oh no, I've got it now. Paul,
yeah,
how do you think? Yeah, how do you think the finish of the aluminium might influence nucleation? Yeah, really, I think Nick, you're absolutely bang on. You know, do we rough up the surface? Do we put? I always thought, you know, crunch up a bit of aluminium foil and put it in there to give lots of surfaces. Yeah, so I haven't got an answer. There's probably some really old papers out there where somebody has done this, but that nucleation bit and the supercooling bit is really, really important. So if you're doing this work in a slightly more advanced way, this was an MSc project that we did, and it was quite nice, and we got some nice results. I would like to see that. Yeah, what are the surfaces? And then the next thing, of course, is you're doing this with a plastic housing. Your phase change materials in a probably a high density polyethylene container. So do you put some of those nuggets in there as well and see how that affects things? Yeah, I think it's a really good question, Nick, which is essentially, will the nucleation provided from the DSE pan affect the bulk behavior and the phase change process? And I think it would be. Yeah, the surface finish would be really, really important. So thank you, Nick, for that question. It's good. I think Jazz is typing. Good. Thanks, Nick. So what I want to do then, I think we've got Gage next up, haven't we? That's going to give us a talk. I'm now going to put this onto my YouTube channel so people can have a look at it. And the aim would be that after a certain number of iterations, we get a kind of format that comes out, we see how the audience grows, and then we start to approach the RSC to get it onto some of their platforms. But I think just before Christmas, hopefully we'll have Gage giving us another really good talk. So thanks, everybody. I'm going to stop the recording. And we're good.
Cool. Thank you. See you in a bit.
Yeah.
Thank you.
Yeah.